So that was the end of Module 3 and the recap. Hopefully you got a little bit from that. If you didn't, hopefully I've been answering your questions in the live chat. But that's it for Module 3. An important module, one that you should definitely pay attention to because a lot of it comes back around. And if you don't know it, it'll just get harder to know it later because you're spending so much time learning the other new stuff in Year 12 that it's hard to find time to go back and just consolidate your understanding. So try to understand it now. I know redox is really hard. I found it really difficult, if you couldn't tell by me constantly stumbling over my words, but it takes some getting used to. So don't stress, do more practice questions and you'll be good to go. But as for now, we're going to get a head start on Module 4, which is drivers of reactions, and we will get started on two specific topics. We're going to be getting started on calorimetry and Gibbs free energy and spontaneity. So these are definitely some of the harder topics in the Year 11 syllabus, just because it's got some things that you've probably never heard of before and formulas that you've never heard of before, and just it's very overwhelming to begin with. So again, as I said in the beginning, the purpose of this kind of head start is just to get you comfortable with Module 4, because Module 4 is very uncomfortable to begin with, and it'll make so much more sense in class if you have a bit of understanding beforehand. So that's the goal. So calorimetry, as I said before, I would talk about endo and exothermic reactions. So endothermic reactions is when heat is absorbed during the reaction. So the energy of the reactants is lower than the energy of the product. So basically, energy is absorbed, and delta H is positive. Delta H, you'll see it everywhere. It's just like, I think of it as like heat, change in heat. Yeah, so the delta means a change in something, so delta H is change in heat. And then we have exothermic reactions, which is when heat is released. So when we look at like the energy of the reactants versus the energy of the products, energy of the reactants is higher because some of that energy ends up being released, so the energy of the products is lower. So that's that. And because of all of this, the delta H is negative. So whenever you see a negative delta H, that's exothermic. A positive delta H, that's endothermic. Lots of reactions that occur are actually exothermic. Endothermic reactions are not rare, but you come across them less often. Exothermic is much more common, especially in the context of the HSC. A lot of the reactions that you see and do, they will be exothermic. An example is combustion, which we talked about earlier today. That's an exothermic reaction that releases heat. So yeah, this is the diagram. These diagrams are very popular in exams. People like to ask their students to explain what's going on in these diagrams. So I'll give a quick little explanation. So delta H in exothermic reactions are negative, and that's because heat is being released and energy is being released. So we start off with reactants, and they have like a certain amount of energy. Then once they react, they obviously lose some of that in the form of heat. Therefore, the products have a lower amount of energy. So that's why the products ends up being lower. On the other side, we have endothermic reactions where delta H is positive, which means heat is absorbed and energy is absorbed. So in the reactants, we start with however much energy we have, and then throughout the course of the reaction, forming the products, we have products with a higher amount of energy than the reactants because it's absorbed some of the heat. So in terms of like physical signs of exothermic and endothermic reactions, exothermic reactions, you'll often feel like heat. You'll feel that like the beaker is getting warm or the test tube is getting warm. That's an exothermic reaction. If it's getting cooler, that's an endothermic reaction. So this is a very common question that you'll get. So this is like heat capacity Q equals MCAT, which is that equation up there. You'll see it everywhere. So Q is quantity of heat, M is mass of substance being heated, C is specific heat capacity, which we'll talk about in a sec, and delta T, is change in temperature. And this is in Kelvin, but really change in temperature in Kelvin and degrees Celsius ends up being the exact same, because it's just how the conversions work. So yeah. So specific heat capacity is the amount of heat energy required to increase 1 gram of a substance by 1 degree Celsius. So yeah, increase the temperature by 1 degree Celsius of a 1 gram of a substance. So most of the time it'll be given to you, unless it's water, where it's also given to you on your data sheet. So for water it's 4.18 joules per Kelvin per gram. And you have to be very careful with your units in this kind of situation, because if the mass is in kilograms, make sure you convert it into grams before using the specific heat capacity. So basically this formula is the cornerstone of all calorimetry that you do. As I said before, the units are very important. Take note of the units, specifically when mass and heat capacity. But yeah, so that's just the formula. We'll look at an example of where you would use this formula, which is heat of combustion. So this tells us how much energy is released when you burn 1 mole of a chemical compound in a combustion reaction. So the steps that you would take to do these, first is you find the change in temperature. And once you do that, it's always given, like it will give you the starting temperature and the finishing temperature. You just work it out by simple subtraction. Then the next thing you do is you use that formula that we used before. Again, make sure that your units match up, because that is a very common mistake. Very common. The reason I keep emphasizing it is just because of how common that mistake is. Like, I've made that mistake before. I'm sure most of my friends have made that mistake before. It's very common. So just trying to drill it into you now so you don't make the same mistakes that I made. But yeah, so heat of combustion, we have that formula that we use, Q equals MCAT. What we need to do first is figure out what the different parts of that MCAT is before finding out the Q. So that includes the number of moles, and then you also need to that includes the number of moles for the fuel being burnt. I don't know why I just had like a brain breakdown just then. Anyway, you need to calculate the number of moles of fuel being burnt, and then you can then calculate the heat of combustion. So we'll look through a practice question. An experiment was conducted to determine the heat of combustion of ethanol. The following data was obtained. We have the initial temp, final temp, change of mass of the spirit burner, and mass of the water. And calculate the theoretical heat of combustion for ethanol. And then it gives us the formula of ethanol, because we'll need that formula to figure out the moles of ethanol that was burnt in that spirit burner. So the process can take a while. First step was to find out the change in temperature, and that delta T is 55 minus 25, which is 30 degrees Celsius. Then the heat capacity formula. This is so important, but the Q equals MCAT. Q equals MCAT. The M is the mass of the water, not of the ethanol, okay? It's the water. It's always the water, in heat of combustion questions, it's always the water. It's not going to be the ethanol. The ethanol, they give you that mass because that's to find out the moles, and that's for a later step. It's the mass of the water. That's why it's in red. It's really important. It's the mass of the water. It's very confusing, but it's the mass of the water. So it's that 102. and then you multiply by 4.18, which is the specific heat capacity of water. That's why we use the mass of water. And then the delta T, and then we get it in joules. So then what we need to do is, what we want to find out with heat of combustion is how many kilojoules per mole is being released. So how we get to that is we need to find out the number of moles, and this is where we use the mass of ethanol. So use the mass, again, another bad speaking moment. So we use the mass of ethanol here, and then the molar mass that we calculated from the formula that they gave us, and then we find it's 0.022 moles. Then what we need to do is, since we want it in kilojoules per mole, we need to change that joules into a kilojoules, and then divide it by the number of moles, and then we get our heat of combustion. So then, again, we have to have that little concluding statement at the end to let them know that we're wrapping it up, let them know that we actually have a final answer. If you're under stress in an exam, it's really easy to have very messy working, and it can be difficult for markers to find your answer, and they might not be able to see it, so that might be a reason that you don't get the marks that you actually deserve. So that's why that concluding statement becomes really important, because you want to make it easy for the markers to see your thought process and see your answer. And they'll be so happy that they can easily get to the answer on your page that they'll easily give you the marks. They won't think twice about it. So it's important that we get that concluding statement in, just because it makes the marker's life easier, and that makes the markers happy, and it will mean that for the rest of the paper they like you and they'll be nice to you. So that's a little trick. Make the markers on your side. I had quite a few messy papers in high school, and when my papers were messy, you couldn't see where my answer was unless I wrote that concluding statement at the end. I could have lost so many more marks if I didn't have that concluding statement, because the marker couldn't find the answer amongst my scribbles. So that's just a little piece of advice, a piece of advice for anyone who under exams just starts being the messiest person alive. Write that concluding statement. It can do you a favor. It can get you some marks that you might have lost if you hadn't written it. So that was the thinking process for that question. Heat of combustion, it can be broken down into two main steps. First is the Q equals MCAT, and then second is delta H equals Q on N being the number of moles. So delta H, I just use for heat of combustion, just H, and that equals kilojoules over moles, so it's Q over N. But Q being in kilojoules, not joules. So that's why I said keep in mind the units, because a very easy place to go wrong is keeping it in joules, but then at the end using the units kilojoules per mole, because that's what you're used to giving as a unit for heat of combustion. So keep that in mind. Convert your joules straight away into kilojoules, because it'll just make life easier. But yeah. So now we'll move on to Gibbs free energy and spontaneity. So this is a little bit tricky, so we'll take it slow. Okay, so part of Gibbs free, again, sorry for the bad talking this whole time. But yeah, Gibbs free energy, it's an equation that's made up of enthalpy, entropy, and also temperature. So we'll get to that equation in a second, but first, what is enthalpy and what is entropy? So enthalpy is H, so that's your delta H. It measures the internal energy of a thermodynamic system under constant pressure. So enthalpy is your change in, it's the same delta H as you've been using for heat of combustion and like exothermic and endothermic reactions. It's the same delta H. So that you're kind of familiar with, but the word enthalpy kind of makes it sound more confusing than it is. But that's enthalpy. And then you have entropy. It's easy to get them mixed up because they kind of sound the same, but they're completely different. So entropy is denoted by S, so change in entropy is delta S, and this is the level of disorder in a thermodynamic system. Now, this is a little bit difficult to explain, but it's all about like randomness and how chaotic the arrangement of something is. So if we have a gas versus a solid of and some type of ionic compound, as a gas, it is much more disorganized because the particles are everywhere. It's in a bigger space, they're bouncing around. That is so much more disorganized than like an ionic lattice. So entropy would be greater in that disorganized gaseous state than it is in that ionic lattice. So it's a measure of the randomness, the disorder. So typically if something starts off as one reactant, so in your decomposition reactions, if you start off with one reactant and you end up with 3 products, that means that as a reaction progresses, you are increasing the entropy because it's becoming more disordered and more like chaotic because you have those 3 products versus the one reactant. So it's a little bit tricky to wrap your head around, but if you overthink it, it just gets confusing. So just know enthalpy, internal energy, entropy, disorder, and that's all you need to know about the concepts. This is like uni level kind of chemistry concepts, so don't read too much into it, don't think too hard about it, because you will get confused, because I got confused thinking too much about it. So yeah, just try your best. But basically how you use this stuff is here. So this is the Gibbs free energy equation. So delta G, which is Gibbs free energy, equals delta H minus the temperature times by delta S. So delta G is change in Gibbs free energy, and that's the unit. Then you have change in enthalpy, and you have change in entropy, and then temperature. And it's very important to note that that temperature is K. It is in Kelvin, it is not in Celsius. Since it's not delta T like it was in our Q equals MCAT, you can't just use Celsius and it will be the same as Kelvin. This is Kelvin. So if you don't know how to convert Celsius to Kelvin, it's plus 273, I believe. So I'll just fact check that for you because yeah, so 273, yeah, it's, you add 273 to your Celsius and that'll be your Kelvin. And yeah, so that's the equation. And basically spontaneous reactions occur without external energy added. So that's what spontaneity means. It means we don't have to do anything, the reactions just happen by themselves. And it favors the formation of products just under the conditions where it's supposed to happen. So if we look at delta G, we have when it's positive, it's not spontaneous. So unlike with the cell potentials, where if it was positive, it was spontaneous, this is the opposite. So when Gibbs free energy is greater than 0, it's not spontaneous. When it's less than 0, when it's negative, it is spontaneous. Another kind of side note about Gibbs free energy is that when it equals 0, it is an indicator of a reversible reaction. So there's that. So here's a practice question for Gibbs free energy and spontaneity. So the question is, for the Haber process, delta S equals minus 200, delta H is minus 2 times 45.92 at 25 degrees Celsius. And then calculate the Gibbs free energy, blah, 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 classify the reaction as spontaneous or non-spontaneous. So, for part A, what you need to do is just use the Gibbs free energy formula. How you do that is you basically just sub in the values, but don't forget that you need to add that 273 to the 25 degrees Celsius to put it into Kelvin, so it's the correct units. Once you sub everything in, you should get negative 32.2 kilojoules. Because it's negative, that means that it's less than 0, obviously. So delta G is less than 0, meaning that it is a spontaneous reaction. So part B is classify the reaction as spontaneous or non-spontaneous. So here, what you would do is you would write that concluding statement that says, therefore the reaction will occur spontaneously, or something simple like that, or therefore the Haber process occurs spontaneously at this temperature. Something along those lines to let them know that you've answered the question and you're done. So that's basically all that you need to do for Gibbs free energy. It's all just using that formula and calculating that formula. Sometimes there'll be extra bits and pieces you might need to do. You might need to calculate delta H using your delta H equals Q on N and then Q equals MCAT. Those formulas, you might have to use that and then use your delta H to be a part of the Gibbs free energy formula. But most of the time you're just subbing in values, and the way that they want to trick you is with the units. So it might be in weird units. Yeah, that's basically, yeah, it will just be in weird units. So in this case, in part A, with the entropy, delta S, we had to convert it into kilojoules, because it's in joules and we want it in kilojoules to go with the delta H, which is in kilojoules. So to do that, they multiplied it by 10 to the minus 3, and then that'll put it into kilojoules for you, and then they subbed it in. So pay attention to the units, because that's where they're going to trick you. If you don't pay attention to the units, then if the number is weird, like you can tell when a number isn't exactly right. If it's way too big or way too small, it's a sign that you probably messed up the unit. So always check your units and always put your units in your like concluding statement or last line, just to let them know that you actually know what you're measuring and you're not just throwing numbers around. So that's that. Some recap of all of that is here in this table. So if we have this equation, which is the Gibbs free energy equation, we have delta G equals delta H minus the temperature multiplied by delta S. So if we look at this, we can kind of figure out what happens at different temperatures and different degrees of disorder. So if we have a very low delta H and we have a very high delta S, we can see that because of the maths, how it will work out is that if you have a low delta H and a high positive delta S, then how the maths will work out is that it will be delta G as a negative. It will always be negative, because if delta H is negative and delta S is positive, just if you do the maths, it'll turn out that delta G is always less than 0. So it will be spontaneous for all t. On the opposite side, if delta H is greater than 0, so if it's an endothermic reaction, and delta S is less than 0, so it's more organized than disordered, then it won't be spontaneous at all t. So if that delta H is much bigger than that delta S, and that delta S is negative, then the negative times the negative will cancel out. It will be positive. It will be non-spontaneous for all t. And then in the yellow sections of the slides, it will depend on whether it's a high temperature or a low temperature. So when it's delta H being positive and delta S is positive, it'll be spontaneous at high temperatures. Then when delta S is negative and delta H is negative, it'll be spontaneous at low temperatures. So these are awesome ways that you can remember and figure out whether something will be spontaneous or not. But then again, you can just plug in the actual numbers into delta G and you'll be able to figure out whether or not it's spontaneous or if it's non-spontaneous.